Hello, my name is Rohan-Paul and very welcome to my computer vision and deep learning YouTube channel. Let's get started. In this video, I will implement the very popular CycleGAN paper from scratch with PyTorch. And as a prerequisite for this video, a couple of days back, I did another one where I discussed in detail the architecture of CycleGAN going through the paper. So if you have not watched that already, I kind of recommend do watch that first because the implementation here in this video will follow that architectural review. I will give the link of that video in the description of this one, and also the length of this video became slightly longer than I thought it to be. That's because I have pretty much explained each and every line of code in this architecture implementation. And all the source code is in my GitHub repository, the link of which is again in the description. Just search by the number because each video in my channel is numbered. One more thing, that over the next month, I will do many GAN or generative adversarial network implementation from scratch with PyTorch. So do subscribe because you hitting the subscribe button is what keeps me motivated to do this. Let's start. First, a quick recap of CycleGAN architecture. So CycleGAN attempts to learn a mapping from one dataset X to another Y, for example, horses to zebras or winter to summer, etc., or Monet to normal photographs. And it does this with two generators, G and F, and two discriminators, dx and dy, corresponding to the two generators. Now, generator G attempts to turn X into Y, and the generator F attempts to turn Y into X. And here again, X and Y denotes images in two different domains. So X could be horses, then Y is zebras. If X is summer, then Y is winter. Similar kind of example. And then dx attempts to differentiate real images sampled from real images X and images produced by the generator F. F is updated accordingly to get better at fooling dx. And then the other discriminator dy attempts to differentiate real images sampled from domain Y and fake images produced by the generator G. G is updated accordingly to get better at fooling dy. And then about the concept of losses in CycleGAN, we have discussed this in detail in the previous architecture video, that we have three losses in CycleGAN. One is the obvious one, the regular GAN loss or general adversarial loss. Then I have cycle consistency loss. This loss is very specific to the CycleGAN architecture, and the cycle consistency loss is added to ensure an image a generator outputs can be mapped back into the original image by the other generator. So mathematically it is represented as this, that is, we have these two generator function G and F, which are also called the mapping function. So the cycle consistency loss will be calculated as f of gx minus x. That is a difference between f and gx and the original image X, and also the G of Fy and the original image Y. So basically the concept is this, that after an original image goes through two cycles of generator function, that is, an X is converted to Y and then Y is again converted back to X domain, then the difference between after the two GAN cycles, the difference between the original image and the reconstructed image, that's called cycle consistency loss. And again, I discussed these concepts in detail in the previous video where I reviewed the CycleGAN architecture. So if you have not seen that, I do suggest do check that video. Anyway, so the next loss is identity loss. This is the third loss in CycleGAN architecture. So this loss is added to help preserve the tint, contrast, or color shade of the image. Basically, conceptually, it states that when given an image of the target class, a generator should return the same image. And that is just defined mathematically as this, that is the mapping function fx, the difference of fx with x, and also the difference between gy and y. And then to measure the total losses, we don't give equal weightage to each part of these three different losses, and that's why the total losses will be an weighted sum of the individual losses, and lambda is a term that is added to define the relative importance of cycle and identity losses compared to the regular GAN losses. we will see these the actual value that lambda takes in our implementation in a moment. And then the generator uses a series of convolution layers and residual convolution layers as well to map one image to another. And the discriminator uses a PatchGAN architecture to classify images. So that was the initial recap of the architecture, and now I'm back in my VS Code. And for the overall structure of the project, I will have three files: cyclegan.py, train.py, and utils.py. And this first one, that is cyclegan.py, will have three classes. That is, the entire actual network of CycleGAN will be implemented in this file. Then utils.py file will have all my utility methods. We will go through them one by one in a moment. And finally, my train.py file will have all the training code. So here all the hyperparameters will be defined, the actual values of them. And then finally, I will run the entire training function from here. We'll go through them in detail. And these three files together will be run with a single and very small Jupyter notebook here. This notebook pretty much doesn't have anything. It's just 3 cells. And because I am running it in Google Colab, so I have to connect my Google Drive in this notebook. And in this Jupyter notebook, you pretty much run this single line, that is Python train.py. So I'm just running this train.py, and this will run the entire project. So that was overall structure. Now let's start. And while explaining the code, I sometimes have to move back and forth between these different files, because some of the methods that I will be using in the cyclegan.py, sometime they are defined in utils.py, things like that. So anyway, so first one is my residual block, and this is a very small method, small class. And why I am structuring it in this particular way, for that first quickly go through the research paper, what they talk about the architecture on residual block. So I am looking at the original paper, and if you go to the very last page, which is the appendix, so that's where the architecture details are here. So what they are saying is that basically we have they are talking about two kind of structure overall. One is with the 6 residual blocks, and another one is with the 9 residual blocks. So I will be mainly following this one, that is the one with the 9 residual blocks here. And then they are clearly saying that RK denotes a residual block that contains 2 3x3 convolution layers with the same number of filters on both layers. So this is what is the important point for building our residual block. I'm just putting a red border around it. RK. And what is RK? So if you look at the network with 9 residual block consists of, I have C7164. This is talking about the normal convolution layer that there's talking about here. C7S1K denotes 7x7 convolution instance norm ReLU layer with K filters and stride 1. Then I have D128 and D256. So these two. So D128 and D256. So what is this? DK. So this is denoted by DK. DK denotes a 3x3 convolution instance norm ReLU layer with K filters and stride of 2. And reflection padding was used to reduce artifacts. And then I have D256 and D1. Sorry, here I have, one second. For my residual block R2561, and I have 9 residual blocks actually, because that's the overall structure I'm looking at. So all these layers starting with the letter R, they are my residual blocks. So I have 9 of them. So all are R256, 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 and so on. And this is where these number 256 denotes a residual block that contains a 3x3 convolution layers with the same number of filters on both layers. So 256 is my number of channels or number of filters. And so back in my VS Code, that's what I'm implementing here. So this is a very simple class residual block. I have one single block defined under nn.sequential. So that means all these is actually a sequential block, and that I'm naming it as self.block. And if you notice that I have starting one reflection pad 2D, and that's again as per the paper, because reflection padding is used in CycleGAN because it gives a better image quality at edges. And then I have a conf 2D, instance norm 2D, then relu, then again reflection pad 2D, conf 2D, and instance norm 2D. Now if you notice that in conf 2D I'm using in channel, and 3. That is, this in channel actually, as per PyTorch's documentation, it is a number of input channels. The second argument I'm using in channel, but actually the second argument represent out channel, or the number of output channels or output filters. Now here I'm using the same because as per the paper it clearly says that same number of filters on both layers. And yeah, 3, and the third argument 3 here represent the kernel size. So this is a 3 by 3 square matrix representing the kernel size. And again in the same conf 2D as well, second conf 2D I mean as well, I'm using in channel 3 because of the same reason that the number of filters remains the same in both layers, and kernel has been defined to be 3 by 3. And then in the forward method of residual block, just because by the definition of residual block here the forward function will be different, that I have to add the residual from my previous calculation, and that's exactly what this is returning. That is x is, then I'm adding the self.block x. So I'm adding the original x to that, the entire this structure, entire this network I'm adding to that, and that's a final return from my residual block. So this entire thing is a single residual block, but I have to implement many of them. And now in this paper they are talking about this network with 9 residual blocks, but somewhere else in the paper they also said that we can increase this residual block if and that is supposed to improve my overall result of this architecture. And that's why we will see in a second in my architecture this number of residual block, which is in hyperparameter, that I'm using 19, and all my hyperparameters are defined in my train.py file in this area here, and I'm using num residual blocks 19. So I'm using 19 instead of 9. So it's a even more deeper network that I'm building here, and that's purely because I wanted to improve the overall accuracy and overall result from my model. So yeah, so that's residual block. The next one is the all important generator network, and that class I'm defining it here. Let's go over them. But first, looking at the network architecture section of the paper again, this entire green and the yellow highlighted area is my generator network. So first I have 7 by 7 convolution instance norm relu layer. Then I have a 3 by 3 convolution instance norm relu layers. Then I have reflection padding, then all the residual blocks, and finally these U128, U64, these denotes this one, that is a yellow highlighted one. UK denotes a 3 by 3 fractional strided convolution instance norm and relu layer with K filters and stride. So this entire thing, this entire structure is my generator class. Now a couple of important points about the generator in CycleGAN, that here the generator consists of encoder and decoder kind of structure. So it first downsample or encode the input image, then interpret the encoding with 9 residual blocks having skip connections. After that, with a series of layers, it upsamples or decode the representation to the size of the fake image. And also in CycleGAN we are using reflection padding, which reflects a row into the padding. It is used mostly for brightness, contrast, and for reducing artifacts. Now a quick word on the reflection padding in general, that there are a couple of reasons to use it instead of zero padding. So for example, on object detection problems, zero padding is usually not an issue, but there are a lot of areas in computer vision where you are looking at things like biological tissue, which can have more of a texture quality than object quality. So if you are trying to mask one type of tissue from another, reflecting will help you avoid edge effects that zero padding might introduce. So that's just one of the situation where you would prefer reflection padding compared to zero padding. And then also in CycleGAN generator, we are not using batch normalization. Instead, we are using instance normalization to normalize across each channel in each data instead of normalizing across input features in a data. So with instance normalization, it allows to remove instance specific contrast information from the image content, which simplifies image generation, and this also results in quite a bit of improved images at the end. So to represent these visually, this is my image here for the generator network, and this is exactly what the paper talks about. I mean, this structure that you see right now is exactly the architecture that paper mentions in its appendix part. So just like what we are talking about, that is a generator consists of encoder and constant part and a decoder. So this is what we see here. Let me zoom in properly here. So as you can see, the representation size shrinks in the encoder phase, stays constant in the transformer phase, and expands again in the decoder phase. Representation size means the input size, the actual shape of the input images, which is represented by the letter K here. And in this case, the dataset that I will be using comes from the famous UC Berkeley CycleGAN dataset, and I will be using winter to summer conversion dataset, and there the image sizes are all of 256 by 256. So just as, let me just go to the paper quickly. So this is what they are talking about. C7S1, this will have 64 of them, meaning 64 filters of C7S1. Then I have 128 filters of these next layer D, which is a 3x3 convolution. And then I have all these 256 residual layers. And finally, I have 128. Now go back to my image here. So that's what we have here, 64 filters of 7x7 kernel size, stride 1, then 128 of 3x3 filters, stride 2, 256 filter of stride equal to 2 and 3x3 size. Then all of these residual one, that is a transformer part of the network, they remain constant at 256 filter of 3x3 size and stride equal to 1. And decoder part, I have this expanding again, so I have 128 filters of 3x3 size, then 64 filters of 3x3 size, and 3 filters of 7x7 size. And the representation, that is the image, input image shape, also goes through this kind of conversion, that is K, then K by 2, K by 4 remain constant at K by 4 across this transformer section. Then again I have K by 2, K, and finally K, and this is the output from the generator. And obviously this output needs to match exactly in terms of sizes the input images. Now going back to my class, yeah. So here that's what I'm doing. So these generator ResNet takes input shape and number of residual blocks as the arguments, and then I'm starting off with my and channels, obviously that will be the coming from the 0th element of the input shape. And in this case, the dataset I will be using, that will be 256. And then I'm starting off with the out channels equal to 64, following my this structure again. Where did that go? Yep. 64. So my first channel number I'm keeping at 64, and then I'm defining this model variable, and this model variable is what I will be continuing to update through these various blocks. So my first block is starting with a reflection pad, then conf2d, instance norm 2d, and ReLU. And following this architecture, I am passing the channels, out channels, and kernel size is 7. This 7 is actually kernel size. Yep. So this is a 7 by 7 matrix here, and that's my model variable. This is this array, and then in channels equal to out channels, because I'll be starting with the next layer here, and my next layer will be these two, D128, D256, and so here the same layer will be repeated twice. That's why I'm running a loop here for the range of 2. I will out channel, I will multiply by 2 for the next one. That's because I have the first one 128, then multiplied by 2 I have 256, and these are my this is the one that DK denotes 3 by 3 convolution, instance norm, and ReLU. So I'm doing exactly the same, conv, instance norm, and ReLU. And in the conv2D, I'm passing in channel, out channel. Filter size is 3 by 3. Actually, I can just mention kernel size equal to 3, and stride to padding 1. This is following exactly what the paper says. And yeah, so that these two layers are over, and finally, well, I'm done with these layers as well. I'm making the in channels equal to out channels from this layer, because now I will be running the next layers, which will be my residual layers. And the residual layers are easy because the same residual layers. So all these are 256. Here they're talking about 9 of them. In my case, it is 19. So I just have to repeat them. So I am just running a single loop here, that is for underscore in range num residual block. This is a hyperparameter that I will be setting in my trend.py file, and in my trend.py file under the hyperparameters variable, I'm setting this num residual blocks equal to 19. So it will run this loop for those 19 times, and each time it will just do model plus equal to residual block out channel. Simple as this, because this whole residual block we already have defined before this one. So this is just will be repeated 19 times, and each time it will be added to my previous output with this line model plus equal to. All right, so now I am done with my residual blocks as well, and only the last section of my model is due, which is my these decoder section or upsampling section. And in this I have these two layers, U128 and U64. And what is this U here? UK denotes a 3 by 3 fractional strided convolution instance norm ReLU layers with K filters and stride half. So let's go back to my code here. All right, so here is the upsampling part. Again, there are 2 of them, and that's why I'm running a loop with a range of 2. Out channel here, because here the out channel will be decreased, and that's why I'm dividing by 2 each time after each layer. So they actually will be U128 and then U64. U. All right, so that's 128 becomes 64 in my second U layer. And again, this is just the upsample layer, and that's why I'm using nn.upsample, scale factor 2, conv, then the regular conv2d, instance norm 2d, and ReLU. In channels, out channels, kernel size, again, remember C, kernel size, and stride 1, padding 1. And finally, after these layers are done, finally I'm updating my in channels to be equal to out channels, because then again this block is done, and now only the last block is remaining. And what is my last block? That is a conv layer, this one, C7S13. Again, this is where this C7S1 is something of a convolution that we started the entire architecture, but this was 64 filter. Now, because this is the final layer, final color image need to be outputted, and hence I have 3 channels here, and they represent a 7 by 7 convolution with stride equal to 1. So that's what I'm doing in the last layer. Reflection padding 2, conv 2d, and tan h. Again, I'm using reflection padding and tan h just as required by the paper. And finally, when all these models are done, that means all my blocks are done. This block is done, then this D128 to D256, this is also done. All my residual blocks are done, upsampling block is done, and a final conv block is also done, and then my entire generator is pretty much done. And now I will be updating the model like this, that is self.model equal to nn.sequential. To that I pass the star model. And finally, so this is because I'm updating the same variable model here, so from the forward function I can just return a model like this, that is model. To that I pass the input x. And also the star, the meaning of the star before the argument model here is a Python syntax. It is used to take in a variable number of arguments. So basically what it allows you to do is to take in more arguments than the number of formal arguments that you previously defined. All right, so that's the end of my generator network, and then my discriminator network, and this is slightly relatively slightly easier. So coming back to the paper again to see the exact architectural details of the discriminator network. So here it is, and the most important part is given here. The discriminator architecture is just this. Let me see, let me put a red border around it. Yeah, so C64, C128, C256, C512, 4 layers, 4 conv layers, that's it. And what discriminator network is that, for discriminator network we use 70 by 70 PatchGANs. We discussed this in detail in the architectural review video. So that is what PatchGAN is. So here let CK denote a 4 by 4 convolution instance norm leaky ReLU layer with K filters and stride of 2. So I have 64 filters conv layer, then 128 filters conv, 256 filter conv, and finally 512 filters conv. Now let's go back to my VS Code and implement that. So let me first put the exact details of the paper here in the comment. That will be my guiding principle. Yeah, so these 4 points: 70 by 70 PatchGANs, convolution instance norm leaky ReLU with K filters. After the last layer I have to produce one-dimensional output, and we do not use instance norm for the first C64 layers. Okay, so the first thing I will do is within my discriminator class I create, and of course discriminator class takes channels height and width as input shape. This is my input shape, and the first thing I will do is defining this block, the discriminator block that will be repeated. All right, before that I also have to define a variable output shape, because this will be my calculated output shape from the discriminator network, and this will be required while I do the actual training inside my train.py file and create my create the vectors for the labels, etc. Then these output shape, which is output shape of image from the discriminator network, this variable will be required. And here I am to define this output shape, I am just using this 1 height divided by 2 into 4 and width divided by 2 into 4. And yeah, so coming back to the discriminator block, this is just creating this thing. That is, in the paper they talk about let CK be a 4 by 4 convolution instance norm leaky ReLU layer with K filters and strides of 2. And what is my K? K will be 64, 128, 256, 512. So K is increasing by a factor of 2 in each layer. So Yeah, so that's what this block will do. In channels, out channels, and normalize equal to true. This is the three arguments it will take, and normalize by default will take the true value. And in my layers variable, I have a conf2d in channel, out channel, kernel size is 4, just as defined by the paper, stride of 2, padding of 1. And to implement this line of the paper, that we do not use instance norm for the first C64 layer. That's what this boolean argument is doing. That is, by default it's true, and when that means in all layers, if normalize is true, then layers will be appended with nn.instance norm true d. But when it is not true, then it will not be appended with this instance norm. So now my discriminator block is this. Ultimately from this, I'm just returning this layer. Yeah. And then in the next step, I am just repeating these discriminator block 4 times, and within nn.sequential. And these 4 times repetition of this is defined to be my self.model, and each time I'm just changing pretty much this out channel, input channel, etc. So the first one is so this will follow this structure: C64, C128, 256, 512. So the first one, out channel 64, then the next one, next layer is out channels will be 128, then 256 and 512. And then there will be a 0 padding added after this. And also note that not listed explicitly in the paper, the model also has a final hidden layer of C512 with a 1x1 stride. So that's my this last one, nn.conf2d in channels 512, because that's coming from the previous channel, and the final output channel is 1. And this is because the paper clearly says after the last layer we apply a convolution to produce a one-dimensional output. So this is what I was talking about. This line was not very explicit in the paper, but this means that I have to start with a 512 channel as in channels for this layer and produce a one-dimensional output, because my discriminator ultimately will just produce true or false, fake or real, this kind of output. So that's this conf2d layer, the final one, where in channel is 512, out channel is 1, kernel size 4, padding of 1. And also note that in the first C64 layer, this is my starting layer of discriminator block. So here I am using normalize equal to false. That means that this line here will be invoked, will be activated. That when normalize equal to false, then the instance norm 2d will not be added for the very first C64 layer. Alright, so that's my entire discriminator architecture, and finally from the discriminator I'm just returning the entire model from my forward function within the discriminator. Alright, with that, okay, I also wanted to show you my discriminator overall structure. So this is the discriminator that we just built. It starts with 256 by 256 by 3 input image. Then this is my C64 layer, C128 layer, C256 layer, and finally C512 layer. And then the final output is fake or not, that is real or fake, that is it's a single dimensional output from the final layer, that is one channel. And that's what we built in here. Now the most important question is, you will ask then, where is PatchGAN implemented? Where do I see the PatchGAN? Let's find that out. So the PatchGAN is inbuilt right in the structure that we just built. These layers, that is C64 to C128, C256, and finally to C512. This is referred to as a 3-layer PatchGAN in the CycleGAN and Pix2Pix nomenclature, because excluding the first hidden layer, the model has 3 hidden layers that could be scaled up or down to give different sized PatchGAN models. So here, to understand these PatchGAN, again I'm just going back to the slide of PatchGAN. So in PatchGAN, given an example of input image of size 256 by 256, the PatchGAN maps from the 256 by 256 to a n by n matrix of output x, where within x, each xij of that n by n matrix signifies whether the patch ij in the image is real or fake. So for example, in this slide, this darker selected blue area, this is one patch, and this is ultimately getting mapped to a fake or real by the end of the PatchGAN network. So noting again here, the main difference between PatchGAN and a regular GAN discriminator is that the regular GAN maps an input image to a single scalar output in the range of 0 and 1, indicating the probability of the image being real or fake, while PatchGAN provides a matrix as the output, where each element of the matrix signifies whether its corresponding patch is real or fake. And in the CycleGAN architecture, the receptive field of the discriminator turns out to be 70 by 70 patches in the input image. So in this slide, this dark blue area, that's one patch, and that is in CycleGAN a 70 by 70 size of patch. So what that means is that PatchGAN architecture outputs a feature map of roughly 30 by 30 points, and each of those 30 by 30 points on the feature map can see a patch of 70 by 70 pixel on the input space, and this 70 by 70 pixel on the input space is called the receptive field size. So in other words, and to be precise, the PatchGAN architecture is equivalent to chopping up the input image into 70 by 70 patches, making a big batch out of these patches, and running a discriminator on each of the 70 by 70 patch with batch norm applied across the batch, then averaging the result. And we can check that in our architecture that we just implemented for the discriminator block, that why I start from this end, that is the output end of my discriminator block, and go backward calculating the input size, I will end up with a 70 by 70 size as the receptive field size for my discriminator block. Let's check that. So this is my discriminator network that we just built a while back. And to check or verify that PatchGAN has been implemented in this, what I need to check, that I will start from the last layer of this discriminator network and go back towards the input layer one by one, and I will see that starting from the end and going back towards the beginning, I will end up towards the beginning with a 70 by 70 size of feature map or 70 by 70 size of patch, and thereby I can verify that the discriminator network is actually working on a patch of 70 by 70 size, and that is, it is starting on a 70 by 70 size from the input image, and at the end of the network it is outputting a single value of fake or real. But first, for that, I need to go back to check the original arithmetic of the CNN feature map calculation. And we all know this formula, that is n output here is the number of output features, n in is the number of input features, 2p, p is the padding, k is the filter size or kernel size, s is stride. So if we rearrange this formula to get my input size from the in output size, I will end up with a different formula, which will be this. That is, here I am so in the previous arithmetic, all these right hand side expressions were given and I need to calculate the in output. But what now, for calculating checking the PatchGAN, my output size is given, stride is given, filter size is given, and I need to calculate the input size, and here I am padding I'm taking to be 0, and this will be the formula. Just so what I'm doing is I'm just rearranging this formula, that is in output multiplied by s, then taking this one here, which will be -1, and with that I will end up with this formula. Now let's do a quick function or quick method to implement this. So this is that function, very simple one. I'm just including this formula, which is the input size given, the output size, filter size, and stride. and then I have to invoke this formula on my discriminator network, starting from the very end of the network and going back one by one towards the beginning. So my discriminator network is this. So I'm looking at this discriminator class that we just wrote a while back, and I have to invoke that formula starting at this end, the very last layer. And the output of the last layer was a single channel, that is as we can see, the out channel is 1, because by the end of the discriminator network it will output a single scalar value of 0 or 1, representing fake or real. So coming back to the method, the first invocation of this method is this: get input size, output size will be 1, filter size 4, stride 1. This remains fixed for my entire discriminator network as per the paper, and only thing I am doing here is output size 1 coming from here. The out channels of the last layer is 1, and that will be my last layer. The output of this entire invocation of this method will be my last layer input, and then this last layer, actually I can last layer input size, this will be my this, and then I can, for the next calculating the next one, that is fourth layer input size, I have to start from here. So here output size will be last layer input size, and filter size and stride remains 1. And similarly, I'm checking the receptive field or the input size for my third layer, second layer, first layer. And each time I am just changing this output size argument of this method, and which will be the input, the output from the previous invocation of the method. That is, a fourth layer input size becomes the output size for the third layer. Similarly, third layer input size, this variable becomes output size for my second layer, and similarly the layer input size becomes the output size for my first layer. And if I run this function, the very last output from this method, from this line, should be 70 by 70. Thereby I can verify that the entire discriminator network is working on a 70 by 70 patch, and by the end of the network it's outputting this single scalar value of 0 and 1. So let's run this cell, and the output I'm getting exactly what I wanted. That is a fourth layer 7, third layer 16, second layer input size 34, and the first layer input size is 70. That's what I wanted. So at the very first, this discriminator network is taking a patch of 70 by 70 size, and then by the end of the network it is outputting 0 or 1. All right, so thereby we just what we did this entire here in this part of the discussion is checking that my discriminator network here is actually implementing the PatchGAN architecture that was talked about in the paper. Now so now with that I am completely done with explaining generator and discriminator class, and now I can move forward for the next section. That is, I have to explain the train, but before that I have to touch upon utils and the data loader methods as well. Let's do that. So starting with the utils.py file, this file has just some utilities method. Let's quickly go through them because they are very standard kind of functions. So the first one, a small method to convert to RGB. It will take an image and convert to RGB format. I'm just using image.new, then giving this argument RGB, and then from the argument I'm taking image.size, and then RGB image.paste, finally returning this RGB image. Next class is image dataset. So this is my data loader method or data loader class, and this is again very standard boilerplate code here, and this is pretty much standard loader that you will see in almost all PyTorch related computer vision projects, where you will have three function. This underscore init, this is the constructor function, a constructor method. Then you will have a get item method, and finally you will have a len method. And in my constructor I am just configuring my the dataset here. So let's quickly check my dataset file structure, then these functions will make sense. So the dataset that I'm using for this project is the pretty popular UC Berkeley CycleGAN dataset. This is the URL for that, and they have quite a few very standard and very popular CycleGAN dataset here. All are super popular here. The like horse to zebra, apple to orange. These are super popular that you will see in many projects implemented. And the one that I am using for this project is this one, summer to winter Yosemite. So I actually this is just two sets of unpaired images, photos, one for summer and one for winter from the Yosemite National Park, and I already downloaded the dataset into my Google Drive, and this is the dataset after unzipping it. So I have 4 folders here: test A, test B, train A, train B. So dataset A and B, and that's how I am configuring my image dataset loader method here in my function. So I am just doing making use of this glob module of Python to join my root folder, and then with the percentage A, and then with the mode, and mode is coming from my arguments, which will be train or test. Basically what I'm doing here is just replicating the folder structure. That is, I will have 2 folders, one for train A, one for train B, and again, depending on the mode, if I change it to test, then it will be test A, test B. That's exactly how my dataset is structured, the folder structure of the dataset. And I'm also passing argument named transforms underscore, and we can define the transforms to be applied in this argument. Yes, and then these get item method. So basically, what this get item method does is that it returns the selected samples in the dataset by indexing. This function is used by PyTorch's dataset module to get a sample and construct the dataset. When initiated, it will loop through this function, creating a sample from each instance of the dataset. So when the sample corresponding to a given index is called, this underscore underscore get item method gets executed. So this method contains a logic for what should be returned when we ask for the indexed data point. Index will be the integer between 0 and the length of the dataset, and the length of the dataset is returned by this method len, which just returning the max of len self.files A and len self.files B in this case, because I have 2 different folders here. And in my this variable image A, that's just my image.open, and from all the files A, I am opening that indexed image. And with this unaligned argument, this is coming from the argument to this class, I can take care of both aligned and unaligned image set in my input dataset. And then here I'm just converting depending on whether the image is in RGB or not. If they are not in RGB, then I'm converting them to RGB. And I'm doing that, of course, for both set A and set B. And finally, I am applying the transforms to my image, and these transforms I will define in my train.py file before the training starts, and we'll go through them in a second. And finally, I'm from this entire class, I'm just returning a dict. The A keyword will contain all the items A, and B will contain all the items B. And now a very important technique that was implemented in this paper called replay buffer. Let's quickly go to the paper to read about that one. So I think that was on page 5. Under the implementation section 4, you will see this training details. So they are talking about second to in here they explain this replay buffer method implementation and what they did. So to reduce model oscillation, we follow Srivastava strategy, and this is another paper that was published by Srivastava, and that's where this replay buffer concept was originally proposed. And in this CycleGAN paper, these UC Berkeley researchers implemented that same strategy of replay buffer. So what they say is we follow Srivastava strategy and update the discriminator using a history of generated images rather than the ones produced by the largest generators. We keep an image buffer that stores the 50 previously created images. So basically, this is a strategy for stabilizing the CycleGAN training, and this replay buffer concept is only used in the discriminator network, and it controls how the generated images are added to the replay buffer and then sampled from it. So basically, the replay buffer returns the newly added images with a probability of 0.5. Otherwise, it sends an older generated image and replaces the older image with the newly generated image. And we will see the implementation in a second. But before that, and the entire thing is done to reduce the model oscillation. Now, before going into the code implementation of this, just quickly go to the original paper, because I went to the original paper that was published in July 2017 by Srivastava and other researchers. And this is where this technique of adding a replay buffer was first published. Let's quickly go to the section. I think that was in page 3 of this. Yes. So this is some images of this paper where this buffer of refined images, the concept of buffer was implemented. So this is the important section where they are talking about this replay buffer, that is updating discriminator using a history of refined images. So another problem of adversarial training is that the discriminator network only focuses on the latest refined images. This lack of memory causes one, divergence of the adversarial training, and two, the refiner network reintroducing the artifacts that the discriminator has forgotten about. Any refined image generated by the refiner network at any time during the entire training procedure is a fake image for the discriminator. Hence, the discriminator should be able to classify all these images as fake. Based on this observation, we introduce a method to improve the stability of adversarial training by updating the discriminator using a history of refined images rather than only the ones in the current mini batch. So this is the main point, a method to improve the stability let me put a border. Improve the stability of adversarial training by updating the discriminator using a history of refined images rather than only the ones in the current mini batch. We slightly modify algorithm 1 to have a buffer of refined images generated by previous network. Let B be the size of the buffer and B be the mini batch size used in algorithm. At each iteration discriminator training, we compute the discriminator loss function by sampling B by 2 images from the current refiner network and sampling the additional B by 2 images from the buffer. Okay, these are some implementation more details. This is not so much important right now for our implementation, but this red bordered one is the most important one, yeah, that's what I implemented. So let's now go back to my code. So here is the code for replay buffer. Basically, we keep an image buffer that stores the 50 previously created images, and in my initializer, that's why I'm doing a assert test here, that is a max size more than 0, then empty buffer, and self.max size is kept at default to 50. And this push and pop is a main method which basically controls how generated images are added to the replay buffer and sampled from it. So first I'm running a loop through the entire data, and data is argument to my push and pop, that will be my input images dataset. And for each element of the dataset, first I'm doing an unsqueeze with torch.unsqueeze, and then if these length of the dataset is less than my max size, then I'm purely just simply adding them into my to return array, because this to return array is a final array that will be returned from this entire class. So if this is less than max size, I have to add it, because because the whole purpose of this class is to store 50 previously generated images. So I'm just adding it here if it is less than the max size length. And then I am checking two things. Before First I'm checking if the probability is more than 50%, then I will be running this block. That is, here the rule is returns newly added image with a probability of 0.5. So first I am doing is just creating a probability distribution from random.uniform, and if that is more than 0.5, then selecting a random index from my max size with this line random.randint, and then I am returning these newly selected or newly generated image, and appending that to my toReturn variable, that is toReturn.append self.data I and cloning will just create a copy of the tensor. And then I also need to replace the older image with the newly generated image, and that is this line. That is, after appending the self.data I, then the self.data I becomes my new element. And what is element? This is each element from data.data. And if this random probability distribution does not generate more than 0.5, then this else clause is activated, and here the rule is otherwise it sends an older generated image. In this case, I have to append the element itself to my toReturn array, which is my final return from this entire class. And finally, I am from this entire class, I'm returning this toReturn by wrapping it within a torch.cat and also a variable, a module of torch. So this torch.cat just concatenates a given sequence of sequence tensors to the given dimension. All right, that's replay buffer. And then the next very important concept to implement is learning rate scheduling in CycleGAN. Let's first quickly check the paper, what they talk about learning rate scheduling here. And they say that we keep the same learning rate for the first 100 epochs and linearly decay the rate to 0 over the next 100 epochs. So the total training will run for 200 epochs, and the first 100 epochs the learning rate will remain same at the base rate or the initial rate, and after from 101 to 200 I have to linearly reduce the learning rate, so that by the end of the training, that is end of the 200 epochs, it becomes 0. And to implement this, the first thing I will do is to use this very popular module of PyTorch for scheduling the learning rate, that is torch.optim.lrscheduler.lambda-r. And the thing to understand here is that this lambda-r function takes an argument called lr lambda that sets the learning rate of each parameter group to the initial learning rate times a given function. That means when I implement this function, each new learning rate will be equal to the old, that is a base learning rate or the initial learning rate multiplied by lambda epoch. And this lambda can be a function or can be an integer, a value to multiply this initial learning rate with. So this is the most fundamental thing to understand. And then let's go back to my utils function to check my implementation. So this is where I'm implementing this concept. It's a very simple method. Let's understand this. And this class basically just returns the original base learning rate if my current epoch is less than 100, and 100 means this one, decay start epoch, this argument. And in this case of the CycleGAN, decay start epoch is 100, very clearly written in the paper. So if the current epoch is less than 100, then just return the original learning rate, that is a base learning rate. And if it is more than the decay, then do this calculation here, that is this line. Just return this line, and how this line is working we will see in a second. But first, in the assert statement of the class, I'm just checking that total number of epoch is minus decay start epoch is greater than 0. That is basically total number of epoch should be more than 100. Only then this whole thing will be applicable, otherwise it will give assertion error. And all right, so now checking for these below line checks whether the current epoch has exceeded the decay epoch. I have put some comments here to make it clear. For example, if the current epoch is 80, then see what happens. Then max 0, current epoch is 80, it will be 80, and self dot offset in this case will be was 0. We'll see that when implementing in the train.py, and minus self dot decay start epoch. So for the epoch of 80, I will get this value within the max function. So max 0, 80 minus 10, 80 minus 100, that is 0, max 0 minus 20, which will return me 0. That means in this entire expression, that is a whole return statement, this numerator part will become 0 in that case. So 0 by something will return me 0. So the step function will return me 1, and that will be the return value from this lambda function. And actually this return value is the multiplicative factor which will be multiplied with my base learning rate, what we saw in this formula here. So the way that these learning rate scheduler of PyTorch will work is that this base learning rate will be multiplied by the multiplicative factor coming out of the lambda function, and that will be my new learning rate. And when it is 1, my original learning rate continues, and that's a case for any value of epoch which is less than 100. Now see what I will get for any value which is more than 100. And now let's say my epoch is 110, which is more than 100. Then see what these lambda function will return. So I have just put these return statement here, and in this case for epoch equal to 100, this will be the calculation 1 minus max 0, 110 plus 0. This offset is remaining 0. We will see that in implementation. Minus self dot decay start epoch, which is 100, divide this whole numerator by self dot number of epochs, which is 200 in this case. In the case of CycleGAN, we will be running up to 200, minus self dot decay start epoch again, which is 100, and this will return me 1 minus max 0 to 10, which will return me 10. That is this expression will become 10 by 100, that is 1/10. So the final output from this calculation will be 0.9. So in the case of epoch equal to 110, my multiplicative factor is 0.9. That means here in this expression, the new learning rate will be decayed or reduced by these factor. That is, the new learning rate will be the base learning rate multiplied by 0.9. And that's how this decay factor will work with learning rate scheduler. Now let's see another example. Say my epoch is 120. In this case, doing the same calculation, I will get the multiplicative factor as 0.8. So my new learning rate will be the initial learning rate multiplied by 0.8. Again, it is decaying, and remember, this initial learning rate is the original base learning rate that we defined at the very start of the training. It is not getting updated. It is not the immediately preceding learning rate. So this learning rate is original base. So that means if I continue reducing this way, then there will come an epoch where my learning rate becomes 0 actually. And that's the purpose of this calculation here. That is this lambda LR function. That is, by the end of 200 epochs, I need to make the learning rate to 0 by continuously decaying from 100 to 200. So to summarize in this line, what we are doing is we are dividing the learning rate equally for the last 100 epoch and keep reducing the base learning rate from 101 epoch up to 200 epoch. And in doing that, because we are dividing the last 100 equally, by the end of 200, the reduction of learning rate will be so much that it will come to the value of 0. Alright, that was about the learning rate scheduling. And the last function, the last method under my utils file is these initialize conv weights normal. This is just to initialize the weights, and the guideline here was very clearly given in the paper. So for the conv layer, I am initializing with the normal distribution, and for the mean and standard deviation, I am taking 0.0 and 0.02, and for the bias layers, it is initialized to some constant, and that's why I'm using init.constant and giving the value of 0.0. And then in for batch norm 2D, I have the normal distribution again, and in this case the mean and standard deviation is 1 and 0.02, And for the bias under batch norm 2D, again it's a constant data initialized with the value of 0.0. So this method I will be using inside my training file to initialize the weights. All right, that's all about my utils files, and now I'm fully ready to run my training. So let's go to my train file. Here, remember this train.py file has a dependence on the other two files because all the methods are defined in the other two files. So that's why I'm importing from utils, import pretty much everything, and from CycleGAN also import everything with this asterisk syntax. And then I'm defining the CUDA because if CUDA is available, I definitely do want to use that. And also related to this, I am also defining a variable called tensor, which will be using my GPU CUDA if my GPU is available. Otherwise, it will be using CPU. And the way you define it is something like this. That is torch.CUDA float tensor if CUDA, otherwise torch.tensor. So the difference that is generally both torch.tensor and torch.CUDA are equivalent. You can do everything you like with them both. The key difference is that just that torch.tensor occupies CPU memory, while torch.CUDA.tensor occupies GPU memory. And of course, operations on a CPU tensor are computed with CPU, while operations on the GPU will use your GPU cores and your virtual RAM of the GPU. All right, so that's about the initial setup, and then these are all my hyperparameters. So I'm just defining a hyperparameter class which will be will return a dict format, and then these are the actual values that I'll be passing to this hyperparameter. So all these epoch equal to 0, n epoch 200, because this is the total number of epochs I will be running. Dataset train mode, train and test. Batch size I'm going to use 4. Remember, this is a relatively larger size of photos that for these summer to winter dataset of CycleGAN. It is 256 by 256 size. And my learning rate, this is the base learning rate, that's kept at 0.0002. Decay start epoch is 100, just as defined in the paper. B1, B2 are bias terms. Number of CPU core I'm using 8. You can change it, of course, depending on your hardware situation. Image size I'm using 128. We'll see where this variable is being used. Channels 3, because these are all color channels. N critic, will come to this later. Sample interval 100. Number of residual, we'll come to these. These are kind of things that will be required for plotting the images. We'll see the usage of this in a second. And number of residual blocks, we are using 19 here. The original paper suggested 2 of them, 6 residual block or 9 residual block, but they also talked about that how you can increase the residual block to make your network even more deeper, and which will improve your overall result. And lambda CYC and lambda ID, these are actually the weightage to be used for my cycle consistency loss, which is 10, and my identity loss, the weight here is 5. We will see this is the pure just the weight. So whatever cycle consistency loss you get, you have to multiply that with 10. All right, let's move ahead. So first here I'm just declaring my root path. I ran these both in Google Drive, and also if you want to run it in Kaggle, because Kaggle has this data set already, then your root path will be the Kaggle root path. So in my case, I'll be using the Google Drive root path mainly because that's what I was running. And okay, so these are some small utility function here again in the train, and these are just for plotting the images. Nothing much to talk about them. These are extremely simple. Like for example, the show image will pretty much just use plt.show, convert the image accordingly from PyTorch to matplotlib, and then just use plt.show to visually display the image. Only one thing to remember here is that note that how I'm getting these PyTorch images in the NumPy format with image.numpy, and then before the final plt.show, I am just transposing the np image variable with np.transpose, and I'm passing 1 to 0. So why is that? And the reason is the PyTorch module. PyTorch modules processing image data expect tensors to be in the format of CHW, channel height width. That's how PyTorch sees its images. So when I have this NP image tensor here, it is in the format channel height width, but Pillow or Matplotlib expect image arrays in the form of HWC, height width channel. So to use the PyTorch image into Matplotlib, I have to convert it or reshape it to put the channel first and then width and height, and that's why I'm doing this transpose 1 2 0. 1 here is my height. 2 is the last parameter in PyTorch, which was width, so I'm bringing it in the second position, and 0, this was representing channel under the PyTorch configuration, and now it will be in the last position. And without using np.transpose, I could have also used plt.im show and then use a permute function. So I could have used something like this, that is plt.im show, that within bracket I pass PyTorch tensor image dot permute 120. It would have done the same thing. And then my next function, these are all small couple of functions. This is to image. Here I'm just using x.view to flatten it, and then I'm taking x.size 0, that is from the image I'm taking 0th element, and then also putting hp.channels, hp.image size, and hp.image size, because here image size means my height and width, and channels is just a number of channels, and all these I'm getting from the top here, hyperparameter things like this. And we will see that where these two images used in a second. And another function, small utility function here for plotting the final output. It is again just nothing, just reading from the path the image and then mentioning a fixed size and then ultimately showing the image. That's all. And then here I am defining some transforms. So very simple transforms I have used only, that is resize my images to hp.img size, here also img size, and then I'm converting all the image tensor to PyTorch 2 tensor method, and also applying normalization with these variables 0.5, 0.5 and 0.5 for all the 3 dimensions of the input image. Similarly, the same thing. So this is my transforms, and then I'm applying the transforms to my train data loader and test data loader, validation data loader. I'm actually naming my test data loader to be validation data loader here. And yeah, so and validation data loader is coming from my image dataset that we discussed in detail while we were discussing the utility function. The very first class was image dataset, which is what passing all the input images to my training model. All right, now I have another small function to save image sample. This is again nothing much to talk about. It is just creating a grid to plot the images. So the save image samples just saves the image in a particular path, and the path will be defined here, and I was saving them in my collab session storage that I will have during the in the virtual machine of collab. Of course, you can define any other path in your local machine or any cloud path in Google Storage, etc. And also note that this function will plot the images after the generator generates the fake images, and that's why I am these gen AB and gen BA, which are my 2 generator objects, they are set to eval mode here. That's because here there is no training going on, and I want to switch off the gradient calculation, and that's why they are set to eval mode. And yeah, so otherwise this function is simple. And then finally, after all the utility function, my overall structure is ready to be trained. But before training, I have to declare all these variables, that is my loss, initialize models, buffers, and criteria, etc. So first I'm defining 3 loss function here. Remember, we have 3 losses in CycleGAN, and the first one is a normal GAN loss, which is here, this line, and then I have a cycle consistency loss, which is in this case L1 loss, that was clearly defined in the paper. So just to show you, I came back to the paper here. This is my cycle consistency loss. We can clearly see that this is the L1 loss that's written here. That one here means it's a L1 loss, and it was written in somewhere else in the paper as well. That here they are just taking the difference between two images produced by the reconstructed image and the original image in the same domain. All right, so that's my cycle consistency loss, and the third one is my identity loss. Again, this was an L1 loss, and remember identity. What is identity loss? That's when to a particular generator I pass the target image itself. That is, say for example, a generator is supposed to generate images in the domain A, and I pass to the generator domain A itself as an input. That means it should not make any changes. That means the image it generates should not have any difference with the target image. So that kind of loss is measured with the third loss in CycleGAN, which is identity loss, and this is an N1 loss. And so those are my three losses. This input shape variable is just for defining the channels, height and width, and the height and width, that is image size, these are coming from the hyperparameter. And then initialize my generator, to generator and to discriminator, the all important two most powerful thing in CycleGAN. So gen AB is coming from my generator resonate class. I'm passing to it input shape and also the number of residual blocks, and same for gen BA. They are actually while creating those two objects, they are actually the same, but while I will the way that I will use it inside my train, that's where they will output different things, because gen AB, that will generate images in the B domain, and because they will generate images in the B domain, to the input of gen AB I have to pass images from domain A. Similarly, for gen BA, they will generate images in the A domain. That means I have to pass as input images from domain B. And for discriminator A and discriminator B, it's obvious they will do the classification for the two classes of images generated by the other two generators. And then if CUDA, so here I am just passing all these gen AB, gen BA, disk A, disk B, and all the three criteria losses to be used to use my CUDA core if I have GPU in my machine. And of course, this CUDA we already have defined at the very top. Where was that? Here, CUDA equal to true if torch.CUDA is available, else false. And then in this section here, I'm just initializing the weights. So all my generator AB and gen BA and the two discriminator will be initialized with these initialize conv weights normal. And also note that I'm using the apply method here to invoke my function that was defined in the utils.py, that is this function, this method, initialize conv weights normal, and that has all the necessary resources within the method to generate the weights. This function does not need anything complex. All right, so my weights are generated here, and then this is where I am creating the buffers, and we discussed this replay buffer function in detail just a while back. So here I am invoking those replay buffer to be created for my fake A buffer and fake B buffer. So this is so fake A will be created by generator BA, and fake B images will be created by generator AB, and these two variables will hold the buffers of those created images, and the buffer size is 50. That is, it will hold the 50 images and will be passed to the discriminator from this buffer. And now defining the optimizers. This is a simple 3 lines of code, because I have a generator, 2 generators and 2 discriminators. I'm actually defining the same optimizer for both my generator, which is Adam optimizer, and learning rate to Adam optimizer is coming from the hyperparameter, betas coming from again hyperparameters B1 and B2. Oops, I just realized while I was explaining the hyperparameter at the very top, I mentioned these B1 and B2 to be biased. No, they are my beta to be passed to the optimizers. And after the optimizers, I have my learning rate schedulers. So this is where I am using this function that we discussed in detail, that is this lambda error class. So again, this lambda error class ultimately will give me a multiplicative factor that will be multiplied with my initial learning rate to decay my learning rate from 101th epoch up to 200 epoch. And that's what it is supposed to do here, though. So I am just declaring three variables for learning rate scheduler G, then discriminator A and discriminator B. And this one will be applicable, learning rate scheduler G will be applicable for both my generators. And all I'm doing that I'm bringing in this torch.optim.lr.scheduler.lambda.lr module, and to that I'm passing optimizer G, and this is the important factor. So this is how it will be implemented. So lr lambda takes a lambda function, in this case that is my lambda lr class, and to that I'm passing my number of epoch. Then this was my offset, and this is my starting epoch from where the decay will start, and to that dot step. This dot step is coming from the definition of the function, definition of the module in PyTorch. All right, with that, all the initial setup is ready, and now my final train method. So I am defining very long, just like in many other GANs. The train method in GAN would be quite long because there are so many steps, so many ways to handle or control the two GANs, that is generator and the discriminators. And here it will be even more lengthier because here I have two generators and two discriminators. And so this is my diff train method. It's quite long. Let's see the length of this. It goes on and on and on. And also it looks slightly longer because I have put very detailed comments inside for you to get it very quickly. So this is my train method, and this takes all these list of arguments. All right, let's start off understanding the steps. It looks very long, but actually it is much easier while you start implementing them, because the steps in CycleGAN are so clear. That is how you control the two generators and two discriminators. So first step, just as usual, I am starting my loop here, and then within each epoch I'm starting another loop for doing my batching, and that is I'm looping over the train data loader, which will give me the index and also the actual input or the batch images. And then I am setting two variables, real A and real B. This will just take the actual images from batch. And remember, from our data loader function, we returned dict. That is, this is my image dataset class, and from here I finally returned this kind of dict. A will have all the items A, which are all my A set images, and B will have all my B domain images. So that's why my real A is accessing them with this A keyword, and real B accessing all the images with the B keyword. And I'm also applying this type tensor so that they are converted to appropriate tensor based on my GPU or CPU. And then in the next two lines, I'm just creating two vectors, this valid and fake. Valid vector will have all its element filled up with 1, which I'm generating with np.once, and the size I'm deciding by this real a.size, and I'm taking the 0th element. And the fake vector will have all elements filled up with 0 because they represent the fake generated images, and again the size is coming from real a.size. And yeah, so then I am putting the generators, I'm switching on the train mode for both gen AB and gen BA. And again, this we remember that is gen BA and gen AB was defined here. So gen AB is my one generator, gen BA is my next generator, and gen AB will produce B domain images, and gen BA will produce A domain images. Very important to remember that, because your training structure will be defined exactly exactly by understanding this, that which generator takes which mode or which domain images, and it generates which domain images as its output. All right, now that both my generator is switched on to train, now I'm this is a standard line optimizer g.0grad, just because going by the usual standard way that PyTorch work, that PyTorch stores gradients in a mutable data structure, so we need to set it to clean state before we use it, otherwise it will have old information from a previous iteration. That's why in PyTorch, for every mini batch during the training phase, this is the typical practice, which is to explicitly set the gradients to 0 before starting to do backpropagation, that is before updating the weights and biases, because PyTorch accumulates the gradients on subsequent backward passes. So if you don't explicitly set the gradients to 0, the gradient would be a combination of the old gradients and the new gradients. That is the old gradients which you already have used to update your model parameters, and also the newly computed gradients. And in that case, the gradient descent will break, that is the descent would therefore point in some other direction than the intended direction towards the minimum. And now create my identity loss, and to do that, the main key point is that I have to pass to the generator the same target level image. That means, for example, Gen BA is supposed to take in images from domain B and generate images for domain A. But I will do the opposite here. That is, I will pass to this the target images, that is real A images, and it is also supposed to create real A images. So that's what I'm doing here. I will pass real A, and then I will see that whether it gives me the same domain image, and that's my identity loss. And so now this function genBA, by taking real A images, will also produce images for the real A, and that the difference between that output and real A, that is my identity loss, and that's I'm calling loss ID A. Similarly, for loss ID B, I will do the exact same thing, but for this is now for real B. So normally gen AB is supposed to take as input real A and produce fake B, but now I will pass real B and see that the output from this function, which will be in the B domain, what is the difference of that output with the actual ground truth real B, and that's my loss ID for B. And then in this line, I am just calculating the average of these two identity losses. And okay, so I'm done with the identity loss here, and then I have to calculate the regular GAN loss, and for that I have to create fake B images by passing real A to my gen AB here in this line. This gen AB will create images in the B domain by taking in real A images. And then for calculating the loss, I also have to bring in the discriminator B, which will discriminate between fake B and real B. So in this line, that's what I'm doing. That is a discriminator B that will take fake B as its input, because it will create a vector of 0 1, that is a real fake kind of vector, and that needs to be so that's my prediction. And this is the actual ground truth that we created already. This vector at the top, valid, is the vector containing all ones, which is my ground truth target values. So that's my loss GAN AB, and then I also have to do the same thing for GAN BA. So I create fake A images by bringing in GAN BA. To this I pass the real B images, which will create fake A, and then to calculate the losses, I have to bring in discriminator A. To that I have to pass fake A. So this is my prediction from the discriminator, which is binary vector 0 containing 0 1 elements, and with that I compare my ground truth, that is valid, and that's my loss from GAN BA. So now I have two losses from my regular GAN The first one is here, loss GAN AB, and the second one is here, loss GAN BA. And now I take the average of those two losses in this line. And next, I'll be calculating the all important forward cycle consistency loss and backward cycle consistency loss. So quickly revisit the original concept again in a second, that cycle consistency loss is a single image has to pass through two generators to create my cycle consistency. For example, their starting position here is a horse image, which is the original domain A image, you can think, that passed through the generator 1 to create my zebra image. Then this output from generator 1 is again passed through the next generator 2 to create back to horse image. So now after the original horse image passes through two generators, it is reconstructed of horse image, and ideally, in the ideal scenario, these two horse image should be exactly the same, but they will not be same in practicality, and to the extent that they are different, that's my cycle consistency loss. So this is what we are calculating here. That's a forward cycle consistency loss, and if we started from here in the opposite direction after two cycles, that would be my backward cycle consistency loss. And here in this code, I am calculating exactly that cycle consistency, forward cycle consistency loss in the first section here. So if we go back to the paper again, just to quickly refer, so this is where they are defining the cycle consistency loss in the original paper, and they are just saying f of gx minus x. It's a L1 loss that they are calculating, and for the backward it will be g of fy minus y. So that's for the first one. That's what I'm doing. So for calculating the forward cycle consistency loss, I have to compare the reconstructed A images with real A images of domain A, and the lambda, that is a weightage factor for cycle loss, is 10, so penalizing 10 times and forcing to learn the translation. That's the purpose of the cycle consistency loss here. So this line is pretty simple, just invoking criterion cycle to reconstructed A and comparing that with real A. And reconstructed A I calculated here by passing generator BA the fake B. So normally generator BA should take real B, but here to generate my reconstructed A, instead of real B, I am passing generator BA fake B. And how was fake B generated? Fake B generated by this line. So if you can see now, this real A images that I'm comparing to calculate my cycle consistency loss for A, that is a forward cycle consistency loss, this real A is going through two cycles of generator. So first real A went through generator AB to produce fake B, and now the same fake B I am using here to pass to my generator BA to produce the original A domain image, and that I am naming as reconstructed A. Now this reconstructed A in the ideal scenario, in the ideal world, should be exactly like real A, because they are generated to be the A domain image. But to the extent these two are different, that is original real A and reconstructed A, that will be captured by my forward cycle consistency loss, which I'm naming in this variable loss cycle A. And now exactly in the similar way, I calculate backward cycle consistency loss as well. So I first reconstruct the B by taking the fake A images through two cycles of generator. So originally fake A was generated here, that is passing real B to gen BA. Now this fake A again is passed to gen AB to produce reconstructed B. And then I calculate the difference between reconstructed B and the real B, and that's my cycle loss B, cycle consistency loss B. And then I take in this line I take the average of these two cycle consistency losses. And so now looks like all my losses are calculated. Now time to create my final generator loss. So this line is does exactly that. And so total generator loss is original GAN loss goes as it is, and cycle consistency loss is weighted by this lambda cycle, lambda underscore CYC. It is coming from my hyperparameter. And then the loss identity is again weighted by this lambda ID, which will be a hyperparameter that will be passed separately. And now I start my backward propagation. So loss G dot backward. And after the backward, I need to update the weights and biases. So the classic optimizer underscore G dot step, this step method will implement this classic function, that is updated theta, that is theta at k plus 1 equal to the previous theta, that is theta k minus learning rate multiplied by the gradient of the loss function, that is y hat, the loss between y hat and y. Okay, so with all these up to this point, all my generator training was going on. So with this final updation of weights and biases, my generator training is done, and now I am into the world of discriminator. And with discriminators, I will have two blocks to train my discriminator. First, training discriminator A here, and then I also have to train discriminator B. The overall structure and flow is exactly the same, so let's go through them. So in discriminator A, first, just like we did in the generator, I have to set my accumulated gradients to 0, and that's what this line does by invoking the zero grad method. And then I have to calculate two losses, my loss real and fake loss. Now loss real is simple, you just pass to the criterion GAN, this is original GAN function, regular GAN function, to that you pass the vector generated by the discriminator classification method, and also the valid vector, that is the difference between these two is my loss real for discriminator A. And remember, this valid, this is just the vector containing all the 1 as its element, because they represent the real images of the ground truth. And now to calculate the fake loss, first I have to make use of the buffer. Well, remember we discussed in detail while discussing this replay buffer method created in the utils.py file, that the generated images don't go directly to the discriminator, they go to the buffer with a buffer size of 50, and then from that buffer storage they are passed to discriminator, to a function that was defined within this class called push and pop. So this function practically just returns newly added images with a probability of 0.5. Otherwise it sends older generated images, and in both cases they are sending images, fake images, to the discriminator for the discriminator to make decision whether they are real or fake. So that's what exactly is what's happening here. That is my fake A is the output of fake A buffer that we defined earlier. On top of that, I'm invoking push and pop, and to that I am passing fake A images. Then these fake A will be passed to my discriminator A. And I'm also bringing in detach method that will get the actual values from the tensor. So that will actually detach the gradient layer or the gradient tree from PyTorch tensor, because I don't need those extra gradient thing to be carried on while I'm doing all these calculation here just for the discriminator, because there is no training going on. I do not need those gradients to be attached, and that's why I'm detaching them here. Anyway, so discriminator A will make a decision on these fake A images by comparing them with the fake images of real and fake, and then that output vector from the discriminator will be compared with fake, which we have defined at the very top, containing all zeros, and that will be my loss fake. And of course I'm invoking the criterion GAN on them, which is my regular GAN loss here. So now I have the total loss for discriminator A calculated in this line, loss real plus loss fake divided by 2. And also remember what the paper says about these discriminator loss calculation. Let's go back. I think it was mentioned here. So yeah, so in practice we divide the objective by 2 while optimizing D, which slows down the rate at which D learns relative to the rate of G. So this is the line, very important, but I have to be honest, I do not exactly understand that how exactly dividing by 2 slows down the optimization of D, and why exactly the researchers did that here. So if you know that, please put that in the comment. And now that my loss disk is, the calculation is done for the entire loss disk A, now do the back propagation with this backward function. Again, these backward function, what they do is just that the del theta will be computed with this single call. That is, del theta means the gradient of theta. And after calculating the gradients with the backward function, I also have to update the weights and biases, and this line does that with the step function. And again, this line, what this line is doing very much is just updating the theta. That is, a new theta at k plus 1 will be the old theta minus, this is actually a minus symbol, minus my learning rate multiplied by the gradient of theta, and the loss between y hat and y, that is the predicted y and actual y. That's what the step function will do. Okay, so that was my discriminator A training, and exactly the same way I have to train the discriminator B. So here in this block, I'm doing exactly that, what we did for discriminator A. So let's go through them quickly. So for discriminator B, exactly just like the discriminator A, first is 0 grad. Always before starting training, you always have to do that to make a clean slate of gradients, otherwise it will be accumulated. Then my real loss is calculated by application of criterion GAN, and to disk B I pass real B and compare that with valid. That's my loss real. And for fake loss, again, first I generate my fake B from the buffer. I don't pass them directly to the discriminator B, but I make use of the buffer function, push and pop, and then generate this buffer, and those buffers I'm passing to my discriminator B and detach the gradients. Then discriminator B will produce a vector of real, fake, things like that. That is 0 1 0 1, etc., and compare that with my fake vector that was defined at the very top, containing all zeros for the ground truth images. And the comparison between them, or the loss between these two vectors, is my fake loss. And then the total discriminator B loss will just be loss real plus loss fake divided by 2. And then I do the back propagation with the backward method, that is calculate the gradient of the loss and also update the weights and biases with the step method. And my final loss D is loss disk A plus loss disk B divided by 2. And with that, my discriminator training is also over. So I'm done pretty much with the main skeleton of the training. The rest of the section is just for logging purpose, and that is when the epoch training is going on one after another. So this part of the code is very short and simple, and no point in spending even more time to explain this, because anyway this video became longer than I thought it to be. So just one thing, these batches done, batches left, it is just a simple calculation that how many batches are done up to this epoch and how many batches are still left, and that I am using to calculate how much more time I am left to it to complete the entire 200 batches of training. And then I'm just printing with all these print statement. I'm just printing the various status or the various statistics during my epoch training. And also I am outputting or plotting the images by using these two methods that we earlier defined, plot output and save image sample. So save image sample will actually save the image sample to my defined path, and then this plot output will just plot the final image that I got up to this point in the training. Alright, so here my training method, this long training method gets over. So the training method started from here, quite a long method indeed. But and then after the method was defined up to here, and then I just need to execute the train method, and I also for the executing of the train method, I also have to pass all these list of arguments, and most of them are coming from my hyperparameters that I have defined at the very top, and a few only other things apart from the hyperparameter is all these generator and discriminator objects that were created from the generator and the discriminator class, and my fake A buffer, fake B buffer, etc. Anyway, these are obvious. So now my all three files are fully ready: cyclegan.py, train.py, and utils.py. Now only thing left is that you have to you have to run this train.py file. So what I did, I created a very small Jupyter notebook. This Jupyter notebook almost has nothing. It's just 3 cells, extremely simple. And because I ran this in Colab, I also connected my Google Drive, because all my data set was in my Google Drive storage. You can of course keep it in the Colab session storage as well, but in that case, when you close the Colab or shut down the session, your data also will get deleted. So in the first cell in this Jupyter notebook, I'm just connecting my Google Drive and checking the current directory and also the list of files in my Colab. The list of files, to run it in Colab, you just need to upload these 3 files in Colab, that is cyclegan.py, train.py, and utils.py. Keep all of them in the same directory, and also Jupyter notebook in the same exact directory like the other files, and then just run this simple command, that is python train.py. This will just execute this train.py file, and because my train.py file is importing all the relevant modules in fact from the other 2 files with these 2 lines, from utils import star, from cyclegan import star. That means you only need to execute this train.py file, and that will start the entire training. So let me quickly show you how the training looks like in Google Colab. But before that, just remember my dataset here was the UC Berkeley CycleGAN dataset. That's very popular, and I have used summer to winter dataset. Obviously, I will keep the link of that in my description of the video. And so the purpose in this training for that dataset was to convert summer images to winter images, and so for that we were given a huge set of summer images and also a huge set of winter images, and through this training on the test dataset, I have to convert the summer test dataset to winter dataset. And when I was running this training in my Google Colab, right after like 2 epochs, I got my generated images look like this. So I ran this only for 2 epochs. Remember, the original training needs to go through 200 epochs. So we can see this is at the very top left, this is the original summer image, and this is the generated fake image, and they are looking similarly for this one, original image, fake, original, fake. And obviously you can see right after 2 epochs we can see reasonably comparable images. Obviously the fake images are still very blurry, we cannot see anything properly, but that's just after 2 epochs. So you can imagine the kind of result I got after 300 epochs. So I will probably show you right now. This is still going on in my separate Colab. And it's quite a GPU intensive. Like for example, in my free Colab version, it almost took my entire GPU, so I could not run it for long. And then I switched on my Colab Pro. There it took almost 15 plus GB of virtual RAM, and that is a GPU RAM. So it's very GPU intensive training in this dataset. So just keep that in mind. But anyway, if you can run up to 300 epochs, you will get very great result with this notebook. And finally, over the next couple of months, I will do many popular GAN or generative adversarial network implementation from scratch with PyTorch. So stay tuned and do subscribe. Thank you very much for watching. See you in the next one.